Hey everyone, today we're going to analyze the two most basic types of circuits, series and parallel. The difference is the orientation of the components, in this case, the resistors. For a series circuit, we have one continuous path for the electrons to flow. For the parallel circuit, we have three paths for the electrons to flow. The electrons will come out of the negative terminal, get split between three different paths right here, and then enter back into the positive terminal. These two different orientations of resistors allows us to alter the voltage and the current for the circuit. And this will apply to different applications.
Now let's pretend that these resistors are light bulbs, and each light bulb is identical to the other ones. If we have a battery, let's say 5 volts, and each circuit here both has a 5-volt battery, so the voltages of each circuit are the same, and we have identical bulbs. Which circuit will have brighter bulbs?
Okay, set up here is a parallel circuit. So I'm going to follow the path right here of the current. So the current's going to come from here, and then it's going to follow this red cord and then split between these three paths. And then they go into the light bulbs. And then the charges will leave the light bulbs, connect back up, and then go back into the power source. So let's switch this on and see how bright it is. All right, pretty bright. And we have 4.9, about 5 volts, and 1.51 amps of current. That's pretty bright. Okay, this is a series circuit. And I'm gonna follow the path of this series circuit. So the charges, or the current is gonna come out of here, out of the red cord. Gonna go into this first light bulb, into this black cord, and it's gonna go into the second light bulb, into this red cord, and then through the red cord into the last light bulb, and then back into the power supply. So let's flip the switch and see, we've got 5 volts, and these light bulbs are significantly dimmer than the parallel circuit. But let's look at the current here. So I think, if I recall, in the parallel circuit, we had about 1.5 amps of current. Here we've got almost a third, or 0.3 amps. So here we've got a relationship between the current of the circuit and how bright the light bulbs are in the circuit.
Comparing these two circuits, we can see that the parallel circuit on the right is significantly brighter than the series circuit on the left. And looking at the currents, the parallel circuit has about 1.5 amps, whereas the series circuit has a little less than a third of an amp. We can see that there's a correlation between the brightness of the bulbs and the amount of current that's flowing in the circuit. But why is that? Why is there more current in the parallel circuit than there is for the series circuit? Well, the answer relies in the resistors and their arrangement. Resistors in series increase the total resistance of the circuit, whereas resistors in parallel decrease the total resistance of the circuit. And the reason is because of Ohm's law. And I'm going to help you understand this using an analogy. So imagine that we are going on vacation. Doesn't really matter where it is, but we have to go through some toll booths on the way there. And the voltage, that's the amount of money that you have in your pocket. So this power source over here, that voltage source, that is the amount of money that you have to spend at the toll booths. These resistors, those are the toll booths. And you have to spend all of the money that you have at the toll booths. So let's say we start with $9. And we have to spend, by the time we get back, we have to spend that entire $9 at the toll booths. The traffic, or the cars on the road, that's the current. And the road itself, that should be the wire. So we have our cars, and we leave our house with our $9 in our pocket. We get to this first toll booth, and we know that there's 3 toll booths that we have to get to. So we can't spend all of our money, otherwise we'll get stuck at the next toll booth. So if all the toll booths are the same, we have to spend the same amount of money at each toll booth. We have $9, so we are going to spend $3 at this first toll booth. A short time later, we get to the next toll booth, and then we have to spend our next $3. Then a little time after that, we reach our last and final toll booth, and we spend $3 there as well. This is just us. Imagine if there were a lot of cars on the road, though. All of the cars that have to go through each one of these toll booths on one single road. Every car has to go through every toll booth. That seems like there would be a lot of traffic jams or a lot of total resistance. Let's see what it looks like for a parallel circuit. We're still going to have our $9 in our pocket, except this time, once we get to the first junction, we get a choice. So we can go through this first toll booth right here, or we can keep going and go through that one, the second toll booth, or we can keep going and go through the last toll booth. It doesn't really matter, we get to choose. Let's just say we choose the third toll booth. Since we only have to go through one toll booth, we will spend our entire $9 at that one toll booth, then leave the toll booth and be on our merry way. What that does, it allows for other cars to go through the other toll booths. If all the cars get to choose one toll booth, that's great. That lowers the resistance because there will be less traffic jams. The last thing that I wanted to show you is to compare the series and parallel circuits in regards to the voltage and current. Recall in a series circuit that there is one path for current to flow. And so the current will leave the battery, go into the first resistor, leave the first resistor, go into the second one, leave the second one, and then go into the third one, leave the third resistor, and then back into the battery. This one path means that the current through each resistor must be the same. Going back to our analogy, all of those cars have to go to each toll booth. That means there's going to be a lot of traffic, but all of those cars have to go through each toll booth, meaning the current through each toll booth or resistor must be the same. But what does it look like for voltage? Remember that our battery is 9 volts. So the positive terminal is 9 volts. That means the negative terminal is 0 volts. We have a potential difference of 9 volts. And that's that electrical pressure that's pushing current through the circuit. The total voltage in this circuit is the sum of all the voltage drops across the resistors. Well, what's a voltage drop? Remember in our analogy that we had $9 to spend, and we had to spend the entire $9 before we got back home. It could be $3 in each toll booth. It could be, $1 at this toll booth, $3 at the next one, and then $5 at the last toll booth. That's all going to be dependent on the resistance of that resistor. But we have to use that entire 9 volts. So our voltage drop is how much money we spend at that toll booth, or how many volts we spend at a resistor. So the total voltage is the sum of all the voltage drops across the resistors. And for the parallel circuit, we still have 9-volt battery. This terminal is 0 volts, so our potential difference or voltage is 9 volts. But since we haven't gotten to a resistor yet, you can think of all of these wires in red at those spots all have a potential of 9 volts. And that potential changes once the current goes through a resistor. Down here, on all of these wires, we're at 0 volts. So the potential, or the voltage, over each resistor is 9 volts. So the voltage across each resistor must be the same. And for current, remember that the current gets to be split up. The current can choose between, going through the first resistor, the second resistor, or the third one, and then it joins back up to go back into the opposite terminal. So we have 3 different paths. So some current can go one way, some current can go the other way, and some current can go the third way. So that will be lower resistance. But the total current is the sum of all the currents through each resistor. So if we wanted to figure out the total current in the circuit, and we knew how much current was going through each resistor, all we would have to do is add up I1, I2, and I3, and that would be the total current in the circuit. That's all. Please reach out to me if you got any questions. Take it easy.